goal of lump capacitance is to determine the temperature of some arbitrarily shaped object as a function of time. In this example, we know the ambient temperature T infinity and some heat transfer coefficient. We're going to assume that the object is initially warmer than T infinity, such that heat is being lost from the object into the surroundings. However, if the objects start out cool, heat would be added to the object and it would warm up over time. Mathematically, they're identical. So a graph of temperature as a function of time, you may already know the solution, but there's some initial temperature, some initial hot temperature, and that decays asymptotically. The dashed line here is T infinity, and it asymptotically approaches T infinity over a long period of time. Some things that we know about the objects are their thermal conductivity, their heat capacity, and their density, along with their characteristic length. Note that a huge assumption we're making is that the temperature is uniform throughout our object. And for that to be true, K has to be some really large value. We need the energy to diffuse readily throughout the object very quickly, such that the temperature is uniform. Another thing that we need to confirm is true is that the length scale is relatively small. And in doing so, if it's a really small object, it's not a stretch to say that the temperature will be uniform. There just isn't as much distance over which the heat has to diffuse. And the third condition that has to be true is that the heat transfer coefficient is relatively small. So we don't want to add heat too rapidly or remove heat too rapidly from the exterior of the object, because that doesn't give enough time for the heat to diffuse uniformly throughout the object. A dimensionless ratio of these three parameters is the heat transfer coefficient times the characteristic length divided by the thermal conductivity of the object. And collectively that ratio is known as the Biot number. And when we use lump capacitance, we have to make sure that the Biot number is much less than 1, perhaps about 0.1 or smaller. So in formulating our expression, we're going to say that all of the heat, the rate at which heat is either being added or removed from the object, is going to be equal to the rate at which the energy is being stored. The amount of energy stored in the object at any particular point in time is equal to the object's mass times its heat capacity times its temperature minus some arbitrary reference temperature. To figure out the rate at which the heat is being stored, we're going to differentiate this with respect to time. The mass of the object is its density multiplied by its volume. So we've got rho times V. The heat capacity we're going to assume is independent of temperature. The reference temperature is just some arbitrary constant value. So we're left with the density times the volume times the heat capacity times the time rate of change of temperature. In our example, the rate of heat transfer is also equal to the heat transfer coefficient times the area of the object multiplied by the temperature at any moment in time minus T infinity, the driving force. Note that there's a negative sign in front of this expression because if the object's warmer than the ambient temperature, heat will leave the object. And we'll start by combining these two expressions and then rearranging to solve for dt dt. Note that at initial times, the difference in temperature of the object minus T infinity, some positive quantity, we find that the slope of our temperature profile is negative. And as time progresses, the temperature difference decreases over time, as does the slope. To solve for the temperature as a function of time, we'll start with our original differential equations, separate them, and we'll integrate it from T initial to some temperature, and we'll integrate time from 0 to some arbitrary time. Upon evaluating the integral, the left-hand side turns into the natural log of this ratio, and the right-hand side is equal to HAT over rho VC. Let's take a moment to check the units in our expression. Because the left-hand side is a dimensionless quantity, the right-hand side had better be dimensionless as well. Let's start with the heat transfer coefficient. H is units of watts, or joules per second per square meter Kelvin. Area has dimensions of meters squared. Time has dimensions of seconds. Density, 1 over the density is cubic meters per kilogram. 1 over the volume is 1 over meters cubed. And 1 over the heat capacity is kilogram Kelvin per joule. Simplifying the units, we'll find that the energy, the masses fall out, volumes fall out, temperatures fall out, meters squared the area, and as does time, we'll find that the right-hand side is indeed dimensionless. Rearranging, we come up with an expression for temperature as a function of time. It's an exponential decay. Let's use this equation to solve an example problem in which we have a sphere made of glass with a radius of 0.1 meters and known thermal conductivities, density, and heat capacity. We also know that the ambient temperature T infinity is equal to 20 degrees C, and the heat transfer coefficient H is equal to 30 watts per meter squared Kelvin. The sphere is real hot to begin with an initial temperature of 500 degrees C, and we want to figure out the temperature at a time of 30 minutes. We know the area of a sphere is 4 pi r squared, the volume of our sphere is 4/3 pi r cubed, and when we plug numbers into this equation, being real careful with units, we'll find that the temperature after 30 minutes is equal to 237 degrees C. And here I've made a quantitative graph of temperature as a function of time, where T infinity is the dashed horizontal line. My hope right now is that you disagree with what I've just done. My hope is that you are saying it is not equal to 237 degrees C. My hope is that you've considered the BO number, which is we've established at the beginning is HL over K, and on our instance, the BO number is about 4.0. And to use this equation, remember, we have to have a BO number that's much less than 1. I'll show you a simulation now that indicates this graph is not true, nor is our temperature of 237 degrees. So what I'm showing right now is an analysis at time equals 0 minutes, and the initial temperature I've set to 500 degrees C. Here's that simulation after 30 minutes has elapsed. We'll find that the exterior temperature is equal to 173 degrees C. Here's the original graph that I showed, which is just a plot of this equation. After 30 minutes, I've superimposed a temperature of 173 degrees C, which is what I find from my simulation. Note that by using lump capacitance, we've dramatically overestimated the temperature of the surface of the sphere. Once we take a cross-section of the simulation, it's a little bit more obvious what's going on. At the center of the sphere, we have a temperature that's almost 500 degrees, whereas on the exterior, the temperature is only about 170 degrees. In this instance, remember, we calculated a BO number that's relatively large, and my take-home message here is that although it's really easy to use this equation, it's also really easy to forget its major limitation in that it's only applicable for very small BO numbers. It could be interesting to look at an animation of the simulation in which we're seeing time elapsing from 0 minutes up to 30 minutes. We see at the end of 30 minutes there's definitely a large temperature spread between the interior and the exterior of the sphere.